Hello math students, today's video is lesson 4.5, features of rational functions. In this video, we are going to talk about the end behavior of rational functions and then use what we have learned about x-intercepts, y-intercepts, vertical asymptotes in order to create a graph of a rational function. So with end behavior, it's a little bit more complicated than with polynomials. So we need to first identify, is my function a proper rational function or is it an improper rational function? If the function is a proper rational function, remember that means that the degree of the numerator, which is the top of the fraction, is less than the degree of the denominator. Every proper rational function has the exact same end behavior. This end behavior is a horizontal asymptote at 0. Or in other words, as x approaches both positive and negative infinity, f of x approaches 0. So proper is pretty basic because it just always goes to 0. If I have an improper rational function, however, so this is where the degree of your numerator is greater than or equal to the degree of your denominator. We have a few more steps that we need to do in order to find the end behavior. So the process that we're going to use for this is very similar to what we did with polynomials. So we need a degree and a leading coefficient. For the degree, what I'm going to do is I'm going to take the degree of the numerator and I'm going to subtract the degree of the denominator. For my leading coefficient, I'm going to take the leading coefficient from the numerator and I'm going to divide it by the leading coefficient of the denominator. The reason I'm doing this, so let's say my function was f of x equals x cubed plus 2x minus 9 all over x plus 1. When I'm doing polynomials, the only thing I care about is the piece with the biggest exponent. So we're going to look at the biggest exponent on top and bottom. If I was to ignore everything else, we would have x cubed over x, which I'm going to subtract the exponent, so it'll be x to the 2 minus 1, which is just, x to the 3 minus 1, which is just x squared. So I'm taking this process right here and I am just cutting out this step and going directly to subtracting the exponents. If I had a coefficient in here somewhere, when I divide them, we're just left with a 2. 2 divided by 1. So once again, I'm taking that step and I am cutting it out. You may run into a case where the degree on top and bottom is the same. So if that happens, what we're going to do, so I'm going to say if the degree of the numerator is equal to the degree of the denominator. So that means when you calculate the degree, we get a 0. There is a horizontal asymptote at the leading coefficient. So writing that with my arrow notation, as x approaches both positive and negative infinity, f of x approaches infinity. Otherwise, for these right here, you're going to use your rules for the polynomials. If you have a positive leading coefficient, that means my graph goes up to the right. If you have a negative leading coefficient, my graph goes down to the right. Even degree, that means the left and right are the same. Odd degree, that means the left and right are opposite. So we're going to use those rules. These next 6 problems ask us to identify the function as proper or improper and then determine the end behavior. So number 1, this is going to be improper because the degree of the top is 2, the degree of the bottom is a 1. So to find the end behavior, I'm going to say, well, maybe my degree now is 2 minus 1, which is 1. For the leading coefficient, my leading coefficient on top was a 1. My leading coefficient on bottom was also 1. So I'm going to go 1 divided by 1, which is 1. I have a positive leading coefficient. So if I write this out in words, I would say it goes up to the right. Odd degree, left and right go opposite directions. So go down left. Or if I write it with arrows, as x approaches positive infinity, f of x approaches positive infinity, up to the right. As x approaches negative infinity, f of x approaches negative infinity, down to the left. For number 2, my degree on top, I get just from the x cubed, so I would say my degree is 3. On bottom, my degree is 1. My leading coefficient on top is a 1. Leading coefficient on bottom is a 1. Because the top degree is bigger than bottom, it's improper. I'm going to use degree is 3 minus 1. Leading coefficient is 1 over 1. So my graph is going to go up to the right because I have my positive leading coefficient. Left and right go the same direction. With my arrows, it would be this. So I go up to the right and then up to the left. Number 3, once again, is improper. But I'm going to change this up a little bit. I'm going to make this an x squared on the bottom. So my degree on top is a 2. Degree on bottom is also 2. The leading coefficient on top is a 1. Leading coefficient on bottom is a 2. When I do the degree, I go 2 minus 2 equals 0. That's an indicator that I'm going to have a horizontal asymptote at my leading coefficient, which is 1 over 2, which I can leave it as 1/2, or 0.5. So I can say for my end behavior that there's a horizontal asymptote at 0.5. I would accept that. Or as x approaches both positive and negative infinity, f of x approaches 0.5. Number 4 is very similar to number 2. The degree on top is 3. Degree on bottom is 1. Leading coefficient on top is 1. Leading coefficient on bottom is 1. So this is improper. My degree is 3 minus 1, which is 2. Leading coefficient 1 over 1 is just 1. So I go up to the right and then opposite on the left because of my odd degree. In arrows, it is this. On number 5, the degree on the top is a 4, degree on bottom is 1. That means my function is improper. So I'm going to look at my leading coefficient on top, which is 0.001. Leading coefficient on bottom is a 1. Degree is 4 minus 1, which is 3. Leading coefficient is 0.001 over 1, which is 0.001. Positive leading coefficient means I go up right. Odd degree means left and right are opposite. Or the left side goes down. So in arrows, it's this. For number 6, my degree on top is a 1. Degree on bottom is a 2. That means my function is proper. So I can either say it has a horizontal asymptote at 0, or as x approaches both positive and negative infinity, f of x approaches 0. So we're going to use this end behavior to help us sketch the graphs of rational functions. So I have a few different examples we're going to look at. For this first one, I have x plus 1 over x minus 2 times x plus 2. Anytime I'm trying to find an x-intercept, you're going to set the top equal to 0. So for my x-intercepts, I want to know where is x plus 1 equal to 0? Well, that happens when x is equal to negative 1. For y-intercepts, you're always going to plug 0 in for x. So replace all of the x's with a 0. F of 0 is equal to 0 plus 1 over 0 minus 2 times 0 plus 2. The zeros don't really do anything. So the top is just a 1. The bottom is negative 2 times 2, which is negative 4. I can either leave it as that fraction or rewrite it as negative 0.25. For my vertical asymptotes, this is where the bottom is equal to 0. So to find my vertical asymptotes, I'm going to find out where is x minus 2 equal to 0. Well, that happens when x equals 2. I want to find out where is x plus 2 equal to 0. That happens when x equals negative 2. To find the end behavior, I need to know, is this proper or improper? Well, my degree on top is 1, degree on bottom is 2, so this is going to be proper. So my end behavior, we can either say has a horizontal asymptote at 0, or we can say as x approaches both positive and negative infinity, f of x approaches 0. Let's go ahead and put this on my graph, what we know so far. I know that I have an x-intercept at negative 1. My y-intercept is at negative 0.25. I have a vertical asymptote at positive 2, so I'm going to put a dotted line there. This dotted line is not actually part of the graph, but it's like a boundary line for my graph. Same thing at negative 2. So my graph is never going to cross a vertical asymptote, but it can, at least in the middle, cross a horizontal asymptote, because horizontal asymptotes are dealing with the ends of the graph, not the middle. What I'm going to do now is I'm going to create what's called a sine line. For this sine line, I am going to use the x-intercepts and the vertical asymptotes. So I'm basically creating a number line here. I'm going to put a -2 for a vertical asymptote, -1, and 2. I don't care how spaced out they are, I just need these numbers. What I'm going to do with this is I'm going to figure out where is my graph going to be above the x-axis and below the x-axis, or where is my graph positive and negative. To do that, I'm going to choose numbers that are in each of these intervals. So I'm going to choose a number that's less than -2, so maybe a -3, and I'm going to plug that in to my calculator. So I'm going to go -3 plus 1. Make sure that you put the numerator and the denominator in parentheses. Divide parenthesis for the denominator and then -3 minus 2 times -3 plus 2. That gives me a negative number, so I'm just going to mark that in that interval my graph is negative. I'm going to choose a number between -1 and -2, so maybe -1.5. -1.5 plus 1 divided by -1.5 minus 2 times -1.5 plus 2. This gives me a positive number. I'm going to choose a number between -1 and 2, so maybe a 0. We've already plugged 0 in for x when we did our y-intercept, and we saw that that was a negative number. Finally, I'm going to choose a number, maybe 3. So 3 plus 1 divided by 3 minus 2 times 3 plus 2. That gives me a positive number. So unless I have either an x-intercept or a vertical asymptote with a multiplicity of 2, my graph will always, my sine line will always alternate positive and negative. If I have a multiplicity of 2, then I would have the same sign on both sides of the graph. So this number line tells me that when x is less than -2, my graph is negative. When x is between -2 and -1, I'm positive. When x is between -1 and 2, my graph is negative or below the x-axis. And when x is bigger than 2, my graph is above the x-axis. So I am going to graph this now. This horizontal asymptote says that when x gets really, really negative, my graph is pretty much on the x-axis. So I'm going to start from the x-axis. When I get close to -2, I have to approach my vertical asymptote. Because my graph has to be negative, I'm going to go down. Between -2 and -1, my graph has to be positive. But as I get close to -2, I have to be close to my vertical asymptote. So I start from the vertical asymptote. At -1, I'm at the x-axis, at my x-intercept. Once I go past my x-intercept, I'm negative, cross through my y-intercept, and then I have to approach my vertical asymptote. For the last section of the graph, I approach my vertical asymptote, and then I go and approach my horizontal asymptote. And that is my graph. We're going to do a similar thing for the last 3 examples. I'm going to adjust number 8 though. I'm going to make it an x plus 4 squared on top. To find my x-intercepts, I want to know where is the top of my fraction equal to 0. So I know where does x plus 4 equal to 0. Well, that happens when x is equal to -4. But because I have this square, I'm going to say it has a multiplicity of 2. My y-intercept, I'm going to replace all the x's with a 0. The top becomes 0 plus 4 squared divided by 0 squared plus 6 times 0 plus 5. So on top I have a 16. On bottom I have a 5. I can leave it like that, or if I want to write it as a decimal, that's a 3.2. My vertical asymptotes happen where the bottom of the fraction is equal to 0. So I need to factor this. So I want to know what two numbers do I have that when I multiply them together give me a 5. When I add them together give me a 6. Well, 1 times 5 equals 6. 1 plus 5 equals 6. So this quadratic factors to give me x plus 1 times x plus 5. So for my vertical asymptotes, I want to know where is x plus 1 equal to 0. Well, that happens when x equals negative 1. I want to know where is x plus 5 equal to 0. That happens when x equals negative 5. This is going to be improper because the degree on top is 2, degree on bottom is also 2. So to do the end behavior for degree, I go 2 minus 2 equals 0. So this is the case where I'm going to have a horizontal asymptote. My leading coefficient on top is a 1, on bottom is 1. So I can either say I have a horizontal asymptote at 1, or I can say as x approaches both positive and negative infinity, f of x approaches 1. When I create my sign line, I have an vertical asymptote at negative 5, an x-intercept at negative 4, and a vertical asymptote at negative 1. So on the graph, I'm going to go ahead and put those on there. So negative 5, negative 4, and negative 1. I'm going to plug a negative 6 in for x. When I do that, it gives me a positive number. If I plug a number like negative 4.5 in for x, that gives me a negative number. If I plug a number such as negative 2 in for x for this next interval, we'll find that also gives me a negative number. And if I plug 0 in for x, which we've already done, I get a positive number. So when I put this onto the graph, I have my horizontal asymptote, it's at 1. My graph is positive when x is less than negative 5, negative between negative 5 and negative 4, negative between negative 4 and negative 1, positive when x is bigger than negative 1. So I need to be approaching my horizontal asymptote on the left. So I come from my horizontal asymptote, and then I have to go up to my vertical asymptote. I'm negative right here, so I come from my vertical asymptote, go up to my x-intercept. I still have to be negative on the left side. We see that because of my multiplicity of 2. I change directions here. Go down to my vertical asymptote. At negative 1, I come from my vertical asymptote and at my horizontal asymptote. So that would be my graph for number 8. When I come over to number 9, this one is improper where the top is bigger than the bottom. To find the x-intercepts, I want to know where is x plus 3 equal to 0. That happens at x equals negative 3. I want to know where is x plus 2 equal to 0. That happens when x equals negative 2. My y-intercepts happen when x equals 0. Replace all the x's with a 0. When I simplify this, the top, the zeros don't really do anything. 3 times 2 is 6. On bottom is a 5. That gives me a 1.2. Vertical asymptotes happen where the bottom equals 0. This is improper because the degree on the top is a 2. On bottom is a 1. My leading coefficient on top is 1. On bottom is also 1. So I'm going to use a degree of 1, leading coefficient of 1. That means my graph goes up to the right, and then the left goes opposite. Or if I write it in arrows, it does this. Let's put it on the graph. So the right side I know goes up, left goes down, have an x-intercept at -3 and -2, a y-intercept at 1.2, and a vertical asymptote at -5. When I create my sign line, I've got a -5, -3, and -2. One thing nice about this type of improper fraction is I know the left side has to go down. So I'm going to be negative over here, positive up here. If I plug in -4 in for x, it gives me a positive number. If I plug maybe a -2.5 in for x, it's negative. So I'm negative, right, when x is less than -5, positive between -5 and -3, negative between -3 and -2, positive when x is bigger than -2. When I go and graph this, I come from the bottom, I go up, change direction, approach my vertical asymptote. I come from my vertical asymptote, go to my x-intercept, go below the x-axis for a little second, go to my other x-intercept, go through my y-intercept, continue going up to the right. I'm not going to go all the way through number 10. If you want to see the worked out example, it's on my website. But if I wanted to find the x-intercepts for number 10, I need to set the top of the fraction equal to 0. Well, when I do that, 3 is not equal to 0, so this one is going to have no x-intercepts. And then I would use the same process that we did on 7, 8, and 9 to find the y-intercept, vertical asymptotes, and behavior, create my sign line, then finish the graph.